Greetings, mathematicians. We have warm-up for day 2. The following probabilities use a deck of playing cards. So we need to determine what is the probability that I select a diamond out from a standard deck of playing cards. The first thing that we have to know is that a standard deck has 52 total cards. So we have 4 different suits. We have clubs, we have spades, hearts, and diamonds, right? So the number of each playing card that I have is 13, because 52 divided by 4 total suits, I get 13 of each suit, right? So here, right, the probability that I get a diamond is just 13, right, because I have 13 total diamonds out of 52. And this actually simplifies. We're going to see this a lot. So 13 over 52, I can divide 13 out on top and bottom. This is a 1/4 chance of happening, right? Which makes sense, right? Because we are interested in what's the possibility of getting a diamond. There's 4 total suits, 1/4. The next one that we have, what's the probability that I get a 5 of clubs, okay? We are specifically interested in one card in particular, which is that 5 of clubs. So there's only one of them, and there's 52 total cards. So the probability is a 1/52 chance. Learning target 22, probability of compound events. Again, our essential questions: how is probability used to determine outcomes? And what are the differences between independent, dependent, and mutually exclusive events? So independent events, this is and. So we have 2 events that do not affect each other. This is anything with replacement. So an example, if I toss a coin and I roll a dice, those events do not affect each other because it doesn't matter what I toss the coin, that's not going to affect the dice roll. So if I roll a single die twice, again, the first roll does not affect the second roll. And how do we calculate that? So it's just the probability of the first event times the probability of the second event. All right, so example 5. A dresser drawer contains 1 pair of socks with each of the following colors. We have blue, brown, red, white, and black. Each pair is folded together in a matching set. You reach into the sock drawer to choose a pair of socks without looking. You then replace this pair, meaning that I put it back into the sock drawer, and we select the second pair. What is the probability that you choose the red pair of socks both times? Okay. So the notation that I like to use, we have probability. So we have probability of red, right? Probability of a red. We put it back, and then we select red again, right? So that's just equal to the probability of selecting red the first time, right, times the probability of selecting red the second time, okay? So I have 5 total pairs, right? So 1, 2, 3, 4, 5. And there's only 1 red pair in there. So the probability of selecting red the first time is 1/5, right? I place it back, so I still have 5 pairs of socks. So we still have 5 pairs of socks. I still have that 1 pair, right? Multiplying fractions, you just multiply the numerators and the denominators. So my answer here is 1/25. Converting to a percent, 1/25, that is just a 4% chance. So not very likely. Example 6, you spin the spinner below and flip a coin. What is the probability that you land on the red 7 and get tails on the coin, right? So the notation, probability that we get a red 7, so red 7, and then we also get a tails. Okay, that's just equal to the probability of getting that red 7 times the probability of getting a tails. All right, and we know how to do these. So probability of that red 7, I'm looking at the spinner on the left-hand side. I have 8 segments. I'm only interested in the red 7, so there's only 1 segment. So that is a 1/8 chance, right? And I'm multiplying that by the probability of getting tails, which is 1/2. And then just multiply straight across. Final answer, 1/16. There is a 1/16 chance of getting that outcome. Pick 2 cards from a deck, one at a time. replacing the cards after each selection. So again, this is really helpful. We have 52 total cards, so 52 cards. And we're selecting a card and we're replacing it. So I want to select a king. I select that king, I put it back in the deck, and then I select a king again, right? So there's 4 kings in a deck, and we have 52 total cards. So the first time is 4 over 52. And the same thing with that second king, right? I still have 52 total cards, and I still have 4 kings, okay? These fractions actually simplify, so 4 over 52. If you look at like the numerical value of a card, there's 13 different cards. So we have ace through 10, so that's 10 cards right there, jack, queen, and king. That's 13 cards. So 4 over 52 simplifies to 1 over 13. And then again, we have 1 over 13. The trick with this lesson is simplify your fractions and then multiply across. So 1 times 1 is 1, and then 13 times 13, we get 169. So we have 1 over 169, which is a very small chance of happening. All right, this next one, we have the probability of getting not a queen, followed by a 7, okay? So probability of not getting a queen, there's a lot of different possibilities there, right? So we have 52 cards. 48 of those cards are not a queen, right? We have 4 queens, 48 of them are not a queen, okay? So we're gonna go ahead and we replace that card, so we still have 52 cards. And then we have the probability of 7, so we have that 4, okay? So again, let's simplify. I can divide out a 4 on top and bottom. So 48 over 52 simplifies to 12/13. 4 over 52 is 1/13. And then just multiply across. Final answer, we have 12 over 169. Okay, last one on this slide. What's the probability of getting a spade followed by an 8 or a 9? Okay, so spade, right, we have 4 suits. We're interested in spade. So we have a 1/4 chance of getting that spade. And then we want an 8 or a 9, right? So there's 4 8s, there's 4 9s, right? So that's a total of 8 out of those 52 cards. Okay, let's make sure we simplify. So this is 1/4. 8 over 52 simplifies to 2 over 13. And then we just multiply across. So our answer is 2 over 4 times 13 gets me 2 over 52. But I see that this can simplify as well, so that is 1 over 26. I actually see right here, so we have that 4 and that 8. Those could cancel out, so this is a 1 and this is a 2, right? So then if I multiply straight across, that should give me my answer. All right, your turn. So a coin is tossed and a single six-sided die is rolled. Find the probability of landing on the heads and also rolling a 3, right? So here's our notation. We have probability of, we want heads, followed by a 3, okay? So that's just the probability of getting heads, followed by probability of a 3, okay? So the probability of heads is 1/2. The probability of getting a 3, there's 6 numbers on that dice, so we only have 1 3, so it's just 1. So we can go ahead and multiply straight across. We have 1/12. All right, dependent events. So the outcome of the first event does affect the outcome of the second event. This is anything without replacement. Here's some examples. So if I have a bag of marbles, right, let's say I have 10 marbles, I grab a marble, I don't put it back in. So that actually affects the chances of the second output because now I only have 9 marbles, right? So that actually does affect the output for the second one. So it's the same calculation, but you need to keep in mind that your numerator or denominator of the second event might change. So a card is chosen at random from a standard deck of 52 playing cards. Without replacement, a second card is chosen. What is the probability that you get, the first card is a queen and the second card is a jack? Okay, so same notation. So we have probability that we have a queen followed by a jack. Okay, so it's the same calculation, probability of the queen times the probability of the jack, but that second jack is going to have one less card in there, right? So the probability of the queen, so we have 4 queens. We start off with the same amount, so we have 52 cards. The probability of the jack, though, we have one less card. We're not replacing it, so we have 51 cards now. We still have 4 jacks in total, though, okay? So we're going to go ahead and simplify, just as we did before. So 4 over 52 is 1/13. And then 4 over 51, I believe, does that simplify? 4 over 51, it does not. So we're going to leave that as is. And we can go ahead and multiply straight across. So we should get 4 over 663. So pick 2 cards, and we're not replacing. Okay, so we have probability of a king and a king. Let's do it. So the first king, pretty straightforward, 52 cards. We have 4 kings. We don't replace it, so we have 51 cards. Be careful. So the first card that we selected was a king. So that means that I have 1 less king to select from, meaning that I have 3 cards left over. Okay, so let's go ahead and make sure that we're simplified. 4 over 52 is 1/13. 3 over 51, that actually does simplify. That is 1/17. So we have 1/17. Okay, now we can just go ahead and multiply straight across. So we have 1 over 221. And notice that your answers for these are very small fractions, right? So we have, it's a very small likelihood of happening, which makes sense, right? Playing cards, there's usually a ton of options, so that's why it's a very small chance of happening. All right. The next one, we are interested in probability of a queen, followed by not a 7, and that is with without replacement. So we have probability of the queen, so we're doing 4 over 52. We have 51 cards then for that second pick, and we're interested in not a 7, right? So if I think about how many cards are not a 7 out of this 51, that is 47 cards, right? Because I have 4 7s in there, but I don't want those. I want the 47 other cards. So let's go ahead and simplify. 1/13 times 47 over 51. This does not simplify very nicely, so we're just going to go ahead and multiply straight across. So we have 47 over 663. 47 over 663. Okay. In a shipment of 20 computers, 3 are defective, 3 computers are randomly selected and tested. What is the probability that all 3 are defective if the first and second ones are not replaced? Okay. So the probability that we have 3 defective. We have defective, followed by another defective, followed by a third defective. Okay, so we're going to take this probability and we're going to do it for each and every single one, keeping in mind that we don't replace. Okay, so let's do it. The first time, we have 20 laptops, right? 20 computers. 3 of them are defective. The second time, we have one less computer to select from. We also have 1 less defective computer, so we have 2. And the last one, we have 18 computers to select from, and we have 1. All right, I'm going to go ahead and look for anything that can simplify. So I see a 2, so that can be a 1, 2 and 18, so I have 1/9. Is there anything else that simplifies there? I see a 3 and a 9, right? So that's 3/9 becomes 1/3. So I can just go ahead and multiply straight across. So 1 times 1 times 1, I have 1. And then 20 times 19 times 3, I believe should get me 1,140. So this is a 1 over 1,000, 1 over 1,140. That is my final answer. Whew, goodness. Okay. All right. Last one for this one. So Mr. Meyer needs 2 students to help him with science demonstration for his class. He has 18 girls and 12 boys. He randomly chooses 1 student who comes to the front of the room. He then chooses a second student from those still seated. What is the probability that both are girls? Okay, so we are interested in probability of selecting a girl followed by another girl, and this is without replacement. Okay, so probability of getting a girl, and then probability of selecting another girl. Okay, so this is how many total students do we have, right? So we have 18 plus 12, that's 30 students, and we have 18 girls. How many students do I have left? I have 29. How many girls do I have left? I have 17. And we're just going to go ahead and multiply those straight across. So this gets me, well, let's simplify. 18 over 30 is 3/5. I can divide out as 6. And then I have 17 over 29. Now I can go ahead and multiply. So I have 51 over 145. Final answer. That does not simplify. That is our final answer.